There. Okay. Okay. I think that should do it. Very good. Okay. All right. Hopefully we solved those technical issues. I don't know if people on Zoom can hear me. Hopefully they can. And is the recording? Yeah, recording is good. Okay. Hi, everyone. So welcome back to campus. And I'm your instructor, Gurudev Dutt, for this course, 1470, Foundations of Quantum Computing and Quantum Information Science. So this is the very first time that this course is being offered by our department. So welcome to being the experiment on this topic. I do research in quantum computing and quantum information. And so I'm kind of pretty excited to be able to bring that to a whole new audience, I think. And as we go along, I would definitely like to learn more about you and where your background is and what brought you to this class. So let me just get started at the beginning with a quick overview of our class, what this course is going to be about, and a little bit about the syllabus, some of which is already in the Canvas side, but I just wanted to go over it in case there are questions, and more about the teaching approach for this class, and finally a little bit of an introduction overview of what quantum information science and quantum computing is. Okay, so that showed up in the wrong order, but that doesn't matter. Okay, so as the title of the course suggests, we're going to be providing you with the basic elements of quantum computing and quantum information science. And this is a mandatory course for those of you who are interested in obtaining this certificate, the undergraduate certificate on quantum computing and quantum information science. Okay, as you all know, since you showed up here, that's the timing for the course. And I have announced office hours right after this class, but also by appointment or anytime really after class, you can always find me, or as I said, also by appointment, you can email me if you have some conflict with the time right after this class, if you want to talk to me. So, okay, so what are the main learning goals for this class? Well, obviously, we want to make sure you come away from this course knowing all the key concepts and the supporting fundamentals. So beyond what you might just read in, a popular science article about quantum computing, we want you to know much more than that, right? That's the point of taking this class. And the applications of quantum information science. And a list of these that I think are key concepts that have been identified by various NSF and other bodies about what are the key concepts in quantum information science. There's a long list here. I'm not going to necessarily read it out, but we will indeed go through all of these over the time of this course. And some of the important resources, well, obviously, one of the big resources is going to be the Canvas site and these lectures, okay? And so I'll be trying to post, if it's slides, I'll definitely post them on the Canvas site, and with notes, I will, of course, with a chalkboard, it may not be possible to put all that on the Canvas site, so please make sure to take good notes, and then various assignments and so on, that'll all be posted on the Canvas site, and you'll probably just upload it back to the Canvas site and I'll grade it there. Okay, the textbook for the class is Introduction to Classical and Quantum Computing by Dr. Tom Wong. There's a free PDF available online, so you're welcome to just use that. I like the printed copy. There's a printed copy, which is very cheap, $15 or something. You can get it from Amazon or from our bookstore. It should be in the bookstore, I think. It was supposed to be there. I don't know if it's shown up yet over there. But yeah, so you can get that pretty easily and cheaply. But of course, I'm going to be drawing from other sources as well, not just this textbook. So your primary material should always be the lectures and the lecture notes and so on. Here's our course outline. It's kind of ambitious, I think, but we'll see how far we get into most of these. Some topics are obviously much more important, and I'll be spending more time on them. And so that might take us, may not be able to get to some of the other topics in here. So I think, again, there's no need for me to basically go through this, but this just gives you an idea of what we are going to be covering in the course. And so you can form your own sort of idea of like whether this course is what you want from, what you want to be in, in this class. Okay, the grading scheme for the class is pretty straightforward, 50% from your homework assignments. Now, I should tell you, like many of the homework problems, the answers are given in the textbook. Of course, any homework problems I assign from outside will not have the answers in the textbook, but so in some sense, it's very straightforward really to do the homework. But I strongly, strongly urge you not to just look at the answer in the back of the textbook, because then you really will not understand the material. And secondly, of course, there are going to be some quizzes, and then also, of course, we'll have some a term project. So the take-home quizzes, I'm not sure if I'm going to have a final quiz yet. We may have one, may not have one. We may just do like 3 or 4 in-class short quizzes. Maybe I'll give you a final take-home quiz or something like that. And then the other major component is the term project and paper, and I'll give you more details as we proceed in the class. Okay, so what is my teaching approach for this class? This is a new class, right? So I've never taught it before. I've taught graduate versions of this class, but this is a sort of new, I'm breaking sort of new ground here for all of us, and you are breaking that ground with me. So I think the most important thing I want to say is that I want to emphasize both the concepts as well as the quantitative tools that you're going to need for quantum information science. And my the biggest motto I have for this class is there are no stupid questions. So please stop me if you have a question, if you don't understand something, and we'll address it in the class. And then, if you still are not following, we can try to obviously talk outside of class and so on, and feel free to come up to me and ask me afterwards about if you didn't understand. And I think what I'm kind of interested to see is, as I bring this to an audience that's not necessarily physicists or other, people who have had quantum courses and so on, I'm kind of excited to see, what it is that I can learn about, teaching this subject, as well as maybe some new ideas in the subject, because I think some of you are from backgrounds that are different than a traditional physics background, which I want to learn more about as well. So, and I think discussions and off-road sort of, we don't have to stick to that big outline that I laid out. If there's some topic that seems more exciting and interesting, I would love to hear you say, hey, we really like this topic. We want to learn more about it. Could you maybe add some material or suggest some readings, and we can talk about it? I'm really open to that in this class, especially the first time we're teaching this, and and this should be fun, and it should engage your curiosity and exploration drives, and that's what I hope will come out of this course. So, and what I expect from you is just much of the same. Just please participate, take notes in class. It's supposed to be a fun class. It's about learning something very new. The idea, this quantum information science and quantum computing, I think what's most exciting about it is this is a very active research area right now, right? This is not stuff from 100, 200, 400 years ago, Newton's laws that you're learning, and everything is established. I mean, lots of things are established, but there's still so much that is unknown and unexplored. And I think that's sort of the challenge for me, because I might teach you stuff that might be obsolete in a couple of years, right? Or a year. But at the same time, there are some foundations that I believe are strong and fundamental, which will not be obsolete. And that's the stuff that that I want to make sure you come away from this class learning about. So yeah, so please just pay attention, take those notes, do the homework, and ask questions. Okay, a few course policies. which are outlined on the canvas as well. The code of conduct, obviously, this is a place for exploration and curiosity and asking questions. So as I've said before, there are no stupid questions, and I want to encourage respectful and productive communication. And there'll be zero tolerance for any kind of, any of these behaviors. And also we have, because a lot of this course is going to involve homework that, as I've said, you can look up the answers, you can, there is a term project, but I want to encourage you, and I say that this is the honor code. I want you to bring that academic honesty and integrity, keep that in mind throughout, and try to follow that. And as I said, we are trying to encourage a good code of conduct. Okay, and for anyone who has any disability issues, please notify me and DRS immediately if you need special accommodations. We'll do our best to accommodate you and make sure you're comfortable. Okay, and our course, like every other one, is fully compliant with Title IX, and I'm a mandatory reporter of any violations. Okay, so before I get started into what quantum information science is, does anybody have any questions about any of this stuff that I've just gone over? Yes.
Is an expectation for like prior knowledge on that being pertaining to like computational systems?
No. We will introduce some of that in this class, and obviously, if you have some background in it, then you might be able to engage it at a deeper level than others, but there's no necessity for it. Some programming experience would be helpful because we will be doing some quantum programming later in the class. And so having a little bit of knowledge of programming, but we will introduce that as well. So hopefully it shouldn't, but the idea of like logic and making some flow of programming and algorithms and stuff will definitely be helpful. But I think most of you hopefully have. Actually, maybe I can poll. I mean, if you don't feel comfortable about raising your hand or not, just checking, like how many of you have some programming experience? Okay, most of you. Okay, excellent. Very good. Okay. So maybe before I get started, I should sort of go around and ask a little bit about you all. So why don't we start from here, and if you can just say your name, what your background is, what your major or whatever your background is, and what you're hoping to get out of this class.
My name is Nada, and I'm actually my background computer engineering, computer science.
Okay.
And I'm looking at this as new 2030, I believe, company if we're going to start developing this.
Yeah.
2023 big research.
Yeah.
So I would like to get fundamentals.
Very good. So
I'm a physics and astronomy senior. I'm getting my quantum computing certificate.
Okay.
I'm Richie. I'm in computer science. I'm just interested. I want to understand some of this stuff.
Yeah, very good.
I'm Tristan, manager of physics, and I'm doing this certificate, and it's here for possible.
Okay.
Joe, I'm a senior computer engineer, and I'm also taking this physics certificate, but more or less I'm taking it because I think it's important to take multidisciplinary kind of engineering and sciences.
Very good.
I'm Brian. I'm a CS major and a physics minor, and so I thought taking this would be interesting.
Good.
I'm Jeff. I'm also CS major. It's my last semester at Pitt, but I'm just interested in learning like the deep, I guess, understandings of quantum outside of the articles that I read.
Yeah.
I'm in computer engineering, and I'm also doing that.
Okay, very nice.
Liam, I'm a senior physics master major. I'm getting a certificate. I'm also doing the grad school for communication science.
Oh, cool.
I'm an engineering science major, and I'm also getting a certificate. Matthew on the comp sci and computational biology.
Mm.
And I'm here for the certificate, but also this stuff is fascinating.
Mhm.
My name's Ryan, and physics and astronomy and math major, and I'm doing the certificate on the
Cool. Either way, it doesn't matter.
I'm Allie. I am an engineering science major, and I'm going
I'm Howard. I'm a physics and computer engineering major, and I'm looking to go to grad school for quantum.
Okay.
I'm Lucas. I'm a sophomore in physics and astronomy. I'm just interested in.
I'm Lily. I'm an engineering science major in Wisconsin. I'm Karen. I'm a physics and astronomy major, and I'm also doing this.
Cool. Okay.
And software physics and astronomy major, and I'm doing the certificate, but I'm also a comp sci
Ah. I think we missed you here in the UCLA show.
I'm
Okay. So who did you cheer for in the in the football game? A little bit of superposition there, huh? Okay. Yeah. Yeah.
Hey everyone, I'm Anish. I'm a philosophy major with background in logic and computer science.
Wow.
Kind of interesting, so.
Who? Philosophy. Nice.
I'm Sean, I'm a physics major, and I'm doing this for the certificate, and then I saw that. My name's Matt, I'm a physics major. I'm Kate, and I'm a sophomore computer engineer. I thought it was cool.
Nice.
I'm here. I'm at computational learning and simulation. I'm here.
Great.
I'm Jacob. I'm studying computer science and statistics. I'm here for the certificate, but also I kind of wanted to learn a bit more about quantum computing.
Very nice. Oh, very diverse background here. So that's very interesting. And also, I hope that will bring some new perspectives also to the topic that I might not have thought about before. I am not sure. I'm sorry, I'm a professor here, so I should know this, but I don't know what engineering science is. So can some of the other people who are in engineering science explain what this major is or what this degree is? Okay. I see.
50% electrical engineering.
I see. Okay, very good. Okay, thanks. Thanks for clarifying that. Okay, so very good. I think this could be quite an interesting mix of people and backgrounds. So let's get started. So most of you are probably or may not be aware, but I would say that we already have had one quantum revolution starting in the 1920s when physicists began to understand what happens at very small length scales with small objects like atoms, electrons, photons, and so on. And they understood the principles of quantum mechanics. And from there, we saw a real flowering of science in all different directions, starting with things like solid state physics and understanding what happened there to of course, nuclear physics with atomics and nuclear physics, and also in things like optics and lasers and so on. So there have been some tremendous inventions that have come out from our deep understanding of quantum physics that happened in the 1920s, which led to things like the invention of the first semiconductor transistor in 1948. And that then, through the application of many engineering principles and lots of hard work by a lot of, on a lot of different directions, we came up with things like the integrated circuit, microelectronics, and also magnetic storage. That's also from a quantum phenomenon. Magnetism is a very quantum phenomenon. And also, as I already mentioned, understanding how lasers work and then being able to build lasers allowed us to then improve our communication networks as well. Right? As you know, most of the data packets that are being sent, like as I'm talking on Zoom here, those data packets are being routed through various communication networks, many of which are optical fibers and lasers are used to transmit that information over optical fibers. So, and the reason for this has been that engineers have managed to double the transistor count that's in your CPUs every couple of years. This is the famous Moore's law. And corresponding to doubling that number of transistors, the size of the features in the semiconductor has gone to increasingly smaller and smaller lengths. So you can see, this was 2010, 32 nanometers. I think we're down to 5 or 8 nanometer. I forget exactly where the next generation of fabs are being built for. But yeah, so we're getting down to extremely small dimensions in the sizes of the features in the semiconductors. And long ago, Feynman spotted that this was going to happen. And Feynman, in case you don't know, is a very famous physicist who won the Nobel Prize and also was responsible for many interesting developments, not only in physics, but also he came up with this idea, which he sort of talked about, which is that as we keep reducing the size of the computer until we get to the level of atoms, now we have to model, or we have to understand the operation of the computer using quantum mechanics. We can't just use classical electrical engineering principles, because at some level, the electrons no longer behave like little particles, but they also have quantum behavior associated with them. Okay. So, and he had an idea for using that, for example, to use the atomic nature or the quantum nature of the electrons or the quantum nature of the atoms in the computer to simulate quantum systems. That was his big idea, that we can maybe simulate quantum systems. And as we'll talk about later, it's actually very hard to simulate quantum systems. And this was a problem that people knew about for a long time and didn't know how to make much progress on it. And I think we are now reaching that stage where this is going to become rapidly possible. And then David Deutsch, who's one of the another huge figure in quantum computing, who came up with the first quantum algorithm, which demonstrates advantage over classical algorithms. He was another one who said, we have to think about computers beyond as just mathematical objects, which was a view that was promulgated by many computer scientists. He said that computers are physical objects and computations are physical processes. So we need to think about the limits of quantum computation or of computation, not just as mathematical principles, but as what physics allows us to do. Okay. So with these two viewpoints, we have reached sort of the dawn of the second quantum revolution. And the idea here is we are going to, so in the first quantum revolution, we used quantum mechanics to predict the properties of many different things. And we use those predictions to maybe engineer, to build, to understand materials better and prepare, new types of devices and so on. But we didn't really leverage three fundamental principles that are at the heart of quantum mechanics that we didn't really use them to build technologies. Okay. We didn't think that there was any use for those principles beyond just using them to predict the properties of materials. And it took, as I said, people like David Deutsch to understand that we can use those principles to build new technologies. Okay. And I'll come to those three principles that are taken advantage of in a minute. But so these breakthrough technologies, what are they? Okay. And that's something that I definitely want you to understand. What are the main applications in quantum information science, or main areas in quantum information science? So I divide them up into these four broad areas. The first one is quantum computing, which of course this course is all about. The second, which is also pretty important, is quantum communication. And then quantum sensing is another extremely interesting and rapidly advancing area. And then quantum simulation. So let me just briefly give you an overview of what each of these are. Quantum computing, I mean, we're going to say a lot about it, but you probably already understand that we're using the principles of quantum mechanics to build new computers, new types of computers. What is quantum communication? Well, quantum communication is using the laws of quantum mechanics to create absolutely secure communication links. Communication that cannot be broken by any other method because it's guaranteed by the laws of quantum mechanics. Okay, and this picture is from a satellite that was put up by China. It's called the Michias satellite in 2019, I think, maybe 2020. I can't remember exactly. 2019, I think. And what this satellite did is to transmit quantum entangled particles between two locations, Vienna and Beijing, and use that to create a quantum video link. Okay, and they were able to like have video messages between the two locations that were absolutely secure, protected by the laws of quantum mechanics. So China is already sort of ahead of us in this regard. Okay, so this is another reason people are very, this is a new technology. We don't want to be left behind. The US doesn't want to be left behind. So we want to encourage, as much research and development and industrial efforts in this area. Quantum sensing is and there are many different types of quantum sensing. This is an area that I work in a lot. But the idea is to use the properties of quantum objects to measure other properties that are hard to measure. So I know that seems like a little, vague, but the idea, for example, if you know about MRI, right, magnetic resonance imaging, some of you might have had to have an MRI or had a family member who had to go in for an MRI, and in MRI, we are using spin resonance signals inside the body to measure what's going on in the body without actually cutting that person open, right? So it's a pretty incredible technology, which came about again. This is an application from quantum mechanics because spin resonance was invented by physicists to measure the properties of nuclei. And now we use it, as I say, for medical applications. And the idea here is to take those kinds of spin resonance and other techniques and apply them to nanoscale objects, for example. This is one application. There are many others that we can talk about. But so that's like what would be really cool is now you could detect what's going on inside a material at very small length scales with extreme sensitivity without actually cutting the material open. And that can be very useful for a lot of applications. And finally, this is another area that people, physicists and material scientists, chemists are very interested, which is the idea of quantum simulation, which is that original Feynman idea that I talked about, that where he said we can use a quantum computer essentially to simulate the property of another quantum system. Of course, some quantum systems are things that only physicists care about, like, superfluids and insulators and so on, maybe. But there are people who care about drugs, right? A lot of people care about drugs and understanding the behavior of drug molecules. It turns out that's a surprisingly hard problem for chemists, okay, to understand why a drug does what it does and how it behaves and the energy surfaces of that drug molecule. And so if you can simulate the drug molecule, which turns out to be an extremely hard problem for anything beyond a few atoms, then you can design maybe better drugs. So this is one exciting possibility. Catalysts are another exciting possibility. So anyway, so there's a lot of excitement about being able to simulate the properties of other quantum systems. So that's sort of the overall 4 broad areas that I think quantum information science is divided into. So here is a sort of list of, impact and applications on the right-hand side, and on the left-hand side, sort of fundamental science that we think could be enabled by advances in quantum information science. So yes, interestingly, people in, say, particle physics, like who deal with quantum chromodynamics and nuclear physics and neutrino physics, are very interested in quantum computers and quantum simulators because they may help us to simulate the behavior of particles, which are very difficult to do in the laboratory and certainly are not possible for current classical computers to simulate. Okay. Black holes and Big Bang cosmology. So in fact, it turns out there are deep connections between quantum information science and what happens at the surface of a black hole. Incredible, right? But that it is a very active and interesting area of research for people. Similarly, Big Bang cosmology, we know that there are many features of the cosmic microwave background that permeates the universe that come from quantum fluctuations that occurred at the Big Bang. And understanding the properties of those quantum fluctuations is a matter for quantum information science. And then metrology, which is another word for quantum sensing. So when I talked about the one application of quantum sensing to be able to like look at objects without cutting them open, another application, it turns out, is in searching for gravitational waves, using the laws of quantum mechanics to make extremely sensitive and precise measurements. In fact, LIGO, which you might have heard of, it's a giant interferometer on Earth, which looks for the presence of gravitational waves that were emanated from black holes and neutron stars, which are billions of light years away. Okay, this was a prediction of Einstein, and only very recently we have observed it a few years ago, and it won the Nobel Prize the next year. Okay, it was that big an achievement. But in fact, LIGO uses ideas from quantum information science to boost the sensitivity. So we couldn't have gotten that evidence of the black hole gravitational waves without some of the advances that were enabled by quantum information science. And then finally, the foundations. These are the things that, at least as undergraduate physicists, physics majors will empathize, the arguments that one has late at night about what really is a quantum state and what is a Schrodinger cat. We may talk about some of that in this class as well, but so those are also being addressed by these quantum information science research. And then, of course, the thing that brings in the grant dollars and has billions of dollars in industry funding is over here, right? This is what people want to achieve with quantum computers and quantum simulators and all the rest. Okay, so I already told you about simulation of molecules, materials, maybe black holes or nuclei, etc. And then then the sort of the more mundane types of, I say mundane, but they're also still interesting. So for example, searching large unstructured databases. This is a problem for classical algorithms. Cryptography, as you may know, there is an algorithm in quantum computing. It's called Shor's algorithm that breaks RSA, which is the current encryption scheme used for a lot of like e-commerce and every other kind of cryptographic application there is. It permeates all over our society right now. And quantum computers, when they become big enough, will be able to break those encryption schemes using Shor's algorithm. And also, of course, I told you about quantum communication. So we could use quantum mechanics to bring back secure cryptography or secure communication by using the laws of quantum mechanics. And then there are also ideas for applying these things to machine learning, which of course is a very hot topic even right now. So anyway, so these are sort of, outlined for you where we think quantum information science and technology might have impacts. But nobody saw the laser coming. Okay, people who knew about quantum mechanics did not think that a laser would ever be built. It popped up, right? And then once the laser was built, everybody was like, well, what use is this? Who cares? Okay, it's a nice little device, but now it's everywhere. Okay, it's in every single, you go to the supermarket, there's a laser in that, in the scanner and everywhere. Okay, so you just don't know what's going to come out of this new science and this new technology. And so, okay, so here are some pictures of real quantum computers. Although I show you this picture, really the device that is at the heart of this, which is the actual quantum computer, kind of looks like that, which is very similar to how, a chip in your classical computer looks like. But this is the sort of the superstructure we need around it to make it work. Okay, so I will talk about that later. And one of the ideas one of the things that we want to do in this class is learn how to program some of these computers. So to this effect, what I've done is I've set up in the IBM Quantum Experience a group for our class, and I will add those of you who continue on in this class, I'll add you to that group so that we get to reserve time on the IBM quantum processors and run quantum algorithms and so on those machines. I told you, I promised that there are three central concepts in quantum mechanics that used to just be talked about, argued about back in the 1920s and 30s. There were famous debates between great physicists about these things, and now we just use them. That's what science is sometimes, right? Things that cause a lot of controversy are now just like, oh yeah, we do that now, okay? So those are these three topics: superposition, entanglement, and measurement-induced collapse. Okay, these three key ideas, and we'll discuss them in this class, are going to be harnessed for quantum technologies. Okay, that's what brings the power to quantum technology. So we'll start with the most basic thing. Okay, and I'm sure all of you know what a bit is, right? In a digital classical computer, it can be represented as just say the state of a switch. When the voltage is on, the switch is closed, and when the voltage is off, the switch is open, right? As an example. And in a modern transistor, for example, a MOSFET transistor like this one, that's just represented by that circuit symbol. But the basic operation is something that you could have done with a switch, right? Well, in quantum computing, we replace this classical bit with a quantum bit, which is called a qubit. Okay, so I will say the word qubit from now on all the time. Of course, this level of understanding that I'm giving you here is probably something you could pick up from a popular science article. So we'll go deeper than this, but I just want to introduce it right away, so you know what I'm referring to. And one example that you might think about is if I take an electron, and let's say I have two little islands where the electron can hop between, okay, that are, say, in a semiconductor material of some type. And the electron could be either on the left or on the right. Okay. So we call this, and I'm going to denote it by this weird looking symbol. Okay. And we'll come back to this symbol later on. But we're going to denote that state by this thing, which I'll call ket. Okay. It's a ket. That symbol is called a ket. But you can just think of it as a zero. Okay. So when the electron is over here, it's a zero. The electron is over here, it's a one. But the weird thing about quantum physics, of course, as I'm sure you've heard many times, is the electron can be in both positions. But not really. What we mean is that the state of the system is mathematically represented by this combination. Okay? It can have some chance of being in zero or some chance of being in one. And that chance will be represented by some combination of alpha and beta, okay, which we'll get to. But people like to say, oh yeah, it's simultaneously on and off. It's not really true, but it's okay to say that, and we might often use that language, but we will make this all more rigorous as we get into the course. So before we get into what this qubit is and how coherence works and how entanglement works and so on, again, stepping back, let's take the big overarching view of what's going on in the field, right? Because this is the first class. So I want you to have that overview of what's going on in the field before we dig deep into any single detail. So quantum computing, it turns out, has multiple architectures, if you like, that we can use to build the quantum computer, okay? And there are 4 standard architectures that have been theorized and think that they can be built. And there are companies working in each of these areas, actually. I should mention that. Research labs, of course, also. So the first one, which I'll call is circuit-based quantum computing, will be very familiar. We'll talk about it a lot in this class. It looks a lot like maybe standard models of digital computing that you might have seen. If not, that's okay. We'll introduce that. Okay. So the second is called measurement-based quantum computing. Okay. And here, this is a different approach, and I'll come back again to this maybe if we have time. The idea is we prepare the system in a quantum state and then carry out a set of like measurements and then feedback, measurement and feedback. So it's kind of like just-in-time quantum computing. So it's like you measure something based on the result, you change what you do on the next step. And based on that, you change what you do on the next step. But it starts with the preparation of a giant entangled state of many qubits, which of course you may ask, how did I do that? Well, that's of course the challenge, right? And there are many approaches to how you might do that. But this is one approach to quantum computing that has been shown to be equivalent to that circuit model of quantum computing. So this is a different architecture, a different approach to doing quantum computing. And we can talk a little bit later on about advantages and disadvantages of these approaches. Then there's another model for quantum computing, which is called topological quantum computing. And this is a very different idea for how to do quantum computing. It looks like nothing like a regular quantum computer that you might write down, which is the idea here. And again, I'm not going to get into the details, but the idea is physicists have known for quite a while that particles in 2 dimensions behave very differently at the quantum level than they do in 3 dimensions. Okay, so in 3 dimensions, you may be aware that the world is essentially divided into 2 types of particles. Does anybody know what they are? What kinds of particles are there in the world in 3 dimensions, or 3 dimensions plus 1 space-time? Any physics majors want to hazard a guess? Yes.
Fermions and bosons.
Exactly. Very good. So fermions and bosons. So without going too deep, idea is there are things like electrons, which are fermions, and there are things like photons, which are bosons, or atoms. Many atoms are mostly just bosons. Okay, and they have a very different, way of behaving. Like bosons like to join up together. They like to be in the same place, in the same quantum state. Fermions don't like each other. They stay away from each other. Okay, and this is in fact the reason why atoms exist. So if all electrons wanted to be in the same place, atoms wouldn't exist. We wouldn't have the kind of atomic structure, chemical bonding, none of this stuff. So the fact that there are fermions is a good thing for the presence of matter, for the presence of life. But at the same time, it means that the world is now very different if you're a fermion or a boson. Okay. Well, it turned out that physicists found that in 2 dimensions, there's another type of particle, or actually there's an infinite set of particles that one could create, which are called anyons. That's because people were like, oh, what do we call them? And somebody was like, oh, I don't know, they're anything, so anion, okay, or anion, I don't know. Okay, and these anions, it turns out, can be used for quantum computing, okay, in a very different way. And the advantage of these anions is, it turns out that they're very protected from noise, from decoherence, which is something that we'll talk about later on in this class. So, okay, so that's another model for quantum computing. It looks very different, right? I mean, look at these lines. They seem to be like crossing and doing all these weird things. Doesn't look like any standard model of computation that you might think about. And then finally, I'll talk, again, I'm not going to say anything more about this. There's something called adiabatic quantum computing. And here the idea is you prepare a system with something like an energy state, and then you let it evolve in a very careful way by controlling certain external parameters. And if you are very clever and you do everything very correctly, you can make that system evolve into the state that you want. And in the process, it does the quantum computation that you want. So again, looks very different from what you might think of in quantum computing. So even if you don't understand any of this, I just want you to bear this in mind. There are 4 different models that we have for quantum computing in current science, current research. And this class, we're going to entirely focus only on this one model, circuit-based quantum computing. And usually when people want to prove that something, say somebody tomorrow comes up with a new model for quantum computer, new architecture, as you might call it, they typically will refer back to this and say, look, I can show you how from my model or my architecture, I can construct any circuit in quantum computers. So that's usually the way of proving that the 2 are identical. Okay, so that's what we're going to talk about. So I just want to keep that picture in mind. There are 4 different architectural models for quantum computing. We are going to stick only to this one type. Okay, and it's useful to keep this in mind because who knows, in a year or 2 from now, somebody might say, you know what, I came up with a completely new algorithm, which I don't know, proves that P equals NP for those who are in computer science, right? Or P not equal to NP, I don't know, whatever. But I can only execute it on a topological quantum computer, or I can only execute it on this new model of quantum computation. And now suddenly everybody's going to throw away all of our quantum computers and start doing that, right? I don't know. I'm just, it's possible, right? I mean, it's always, that's why we are doing research in this area. So again, at a very high level, you need to know that there are many different physical realizations of qubits. Okay, I showed you a qubit as an electron in a left or right position, but that's not actually how qubits are created in the lab, in the chip, etc. Okay, So broadly, just so you know the words here, I'm putting up these words. We'll go back to these in a while, but they are, one of them is the trapped ion qubit. Then spins in solids, spin qubits in various semiconductors and materials, solid materials, superconducting circuits. And then this is actually a topological qubit. It's called a Majorana qubit in a nanowire. Excuse me. And neutral atoms. So neutral atoms and ions sort of similar. One is an ion, one is an atom, but just the way that they're manipulated and the way they create quantum operations is very different. And then photonic circuits. So all of these are sort of, I would say, we don't know yet where the winner is going to be. At the moment, the state of the art are probably, I think this I have to declare, I think it's 127 now. So there are 127 qubit processor that IBM has come out with. I think Google has a 72 qubit, maybe something bigger than that. I have to check again their latest processor, IonQ, which does trapped ion. So these two are superconducting quantum computers. Okay, this one is a trapped ion quantum computer. And I should include some of the neutral atom ones. They have many qubits as well now. Okay, they have like 100 or so, but they haven't demonstrated every single thing in quantum computation yet. But anyway, so the idea is that we know that these are definitely some state-of-the-art quantum computers that you're looking at in these images. And I think it's kind of useful to step back here for a second and say and ask, why don't we know? Why are we still figuring this out? You know, what's happening? Like, why don't we already know which one is the best? Let's put, you know, all of our money into that and let's make it happen, right? Well, so for those of you who know a little bit of the history of classical computers, this is not so surprising. From the beginning, when the first sort of classical computer idea was created by Babbage in 1833, it took almost 100 years till we got to something that is like a more modern version. You know, this is the Colossus. This was the first sort of vacuum gauge based or vacuum tube based type of. It wasn't a general purpose computer. It was created for the purpose of like breaking codes in World War II. You know, but it had all the trappings of a modern computer. And then, of course, the first sort of general purpose programmable computer was ENIAC, 1945. So that's almost 100 years there, just to get to something that begins to look like, you know, what a modern computer does, right? And then we had the invention of the first transistor. But if, in case you don't know, the first transistor was invented in a material that we no longer use, okay, for transistors. It was invented for germanium, okay? And as you know, most of our processors are silicon-based, okay? Then this is, I think, the first sort of microcomputer that was created with those germanium transistors, okay? Harville Cadet in 1955. And it took another 15 years or so before Intel made something that looks a lot closer to our current computer. Okay, this is the 4004 4-bit CPU. It had 2300 transistors, a huge advance, right? Imagine you came from there to here, right? It's a small, it fit in on your finger, right? And then very quickly though, after that, things began to change. That's a factor of 10 already, a couple years later, 7 years later, factor of 10 improvement. This is the Moore's law starting to take effect. And now we have this, right? 33.7 billion transistors fitting inside one of these computers, right? As a microprocessor. I took what, 1833 to 2020 till we have one on every desk in our pockets, you know. So took a while. Okay, so it may not be so surprising, but now that we have the advantage of classical computers, I think the timeline for quantum computers is going to be faster because we have these amazing tools now. We have these amazing computers and artificial intelligence tools and programs and ways of thinking about computation that we did not have, say, 100, 150 years ago. Hopefully it'll be faster. We don't know. Okay. Any questions? I've been talking for a while. Yeah.
When would we expect to see Moore's law take effect on it?
Ah. Oh. I mean, I think in some way we are starting to see it. I mean, like, the Google microprocessors were like, I'm trying to remember now. The first ones are probably like 12, 15 qubits. Not very long ago, 4 or 5 years ago. Already we're up to 72, or 127 with IBM, Doesn't seem like a lot, but again, we're going sort of exponentially. I think the harder problem with quantum computers is that as you scale, we will talk about this, is we have to control the noise, the environment, keeping that qubit pristine. That is a big challenge. That's why we had that big, I showed you that big structure. It's a refrigerator. What that refrigerator does is it cools the chip, the superconducting chip, down to a few thousandths of a degree, okay, a few millikelvin. Okay, so just a little bit above absolute zero. So it's much, much colder than outer space. Okay, outer space is like 2.7 Kelvin or 2.1 Kelvin. Okay, and these superconductors are sitting at a temperature that's 1,000 times lower than that. Okay, and okay, so that's superconductors, and the ions that I was talking about, they are in an ultra high vacuum. Okay, extremely isolated from the rest of the world in an environment. And the reason for the cold, as I said, is just to protect it from lots of types of things that can disturb the quantum state. Okay, same thing with the atoms. They're at room temperature, but they're sitting in the vacuum so that they don't get perturbed by anything outside from the world. Okay, it turns out the spins that I was showing you here. Let's go back a little. The spins in solids, there are two types. In silicon, there are some spins. Those also have to be cooled, but they tend to have much longer coherence times. So I've sort of gotten away from but stop me if any of this seems like you don't understand any of the words. Think of coherence time as how long the system remains quantum, okay? And if it stops being quantum, then it's no use. It's become a classical random computer at that point, okay? And we don't want that. So keeping it quantum is one of the biggest challenges, right? And yeah, so these spins in solids, in silicon, actually, it turns out, they remain much more coherent than the superconducting circuits. Okay, they can even be seconds, which seems very short, but is like a very long coherence time. Okay, and these, which are the spins in solids that I work with, these are called nitrogen vacancy centers in diamond. They stay coherent quantum for seconds at room temperature. Okay, so why aren't we building quantum computers out of these? Well, we are trying, right? There's some challenges along the way. Okay, but we are trying to build quantum computers from those. And this I told you about the topological. These also tend to be very cold. The neutral atoms, yeah, they are also in this very high vacuum, and they're protected from the environment. Now, photons, it turns out, can operate at room temperature. They can take advantage of the scalability of CMOS fabrication that we have for our modern silicon technology, but they have some disadvantages with coherence time, with creating, gates between the photons and so on. Okay, so we'll come back to all this, but I'm glad you asked. So this is the challenge, right? How to scale, how to get that Moore's law going in our favor is going to be a combination of all of these things somehow. We have to protect the quantum system, we have to scale it up. And so there are a lot of challenges in that area. So here's a timeline for quantum computing, where we are sort of in the quantum era, okay? The second quantum revolution. So 1981, Feynman proposes this building of quantum computers. David Deutsch in 1985 describes the universal computer based on quantum physics. Peter Shor's algorithm is probably the first quantum algorithm that people saw was solving a problem that was very practical. That was an important classical problem that hadn't that had no good algorithm. And then from there, we've had, the first 2-qubit quantum computers, 7-qubit. This is in a system that, we don't think will be very useful for quantum computing now, but at that time, it was the first in principle demonstration. Okay, and it just, continues from there. So we are about 20 years here, right? 1998, from the first 2-qubit quantum computer to now 2022, right? So it's only been about 20 years of work in building quantum computers. So we have, some ways to go. So what is it that we could do if we built a quantum computer? Why are people so excited about quantum computers? Right? This is one question that you'll probably understand. I've talked about some of the applications, but where is the power of these quantum computers coming from? This graph, I know it's very busy, so sorry about that, but I just wanted to illustrate where the sort of the excitement for quantum computers comes from. Okay, so the idea is, so if in case you know a little bit about RSA encryption, the algorithm that we use to encrypt, all the communications, e-commerce, etc., everything that we do for modern cryptographic protocols, RSA relies on something which is that it's easy. Once you're given the factors of a number, it's easy to prove that that is the factors. You just multiply them together. And multiplication is a very quick operation in normal computers. But if I give you the product and tell you to find the factors, that's a very difficult problem, mathematically, okay, or algorithmically, whichever way you want to call it. So in fact, there's one main algorithm that we know. It's called the number field C, which is denoted by NFS over here. Okay. And so the NFS, what it does is it scales exponentially with the number of digits of the number that you're trying to factor. So this is in binary digits, but you can convert that pretty straightforwardly to decimal digits. So like, maybe on the next slide, I'll show you. So this is 160 decimal digits. This was done in 2003, the factorization of that number. That took 8 core years. So just think of a core year as a processor running at some speed, I forget, maybe 1 gigahertz or less. It took 8 core years for that computation to happen with 160 decimal digits. You go to 232 decimal digits, that went from 8 to 2000 core years. So factor of less than 2 almost, right, in the number of digits took 1,000 times almost, well, not quite 1,000, but you see, like a couple orders of magnitude. A few more digits and the algorithm improved a little. People figured out some efficiencies. They were able to do this one in only 2,700 core years. Okay. But current modern day RSA is RSA 2048. Okay. It's 2,048 decimal digits. Okay. That's going to take over billions of years on the same scale to crack. Okay. So that's the kind of problem that factoring the numbers in an RSA encryption is. That's how hard it is for a classical algorithm. So I'm going to step back to the earlier slide. This is predictions using Shor's algorithm with different architectures of quantum computers and so on. It's not important. The point is, you can see if I take any given bits, and I pick some very, reasonable, let's say 1 hertz, 1 hertz, that's 1 second, for a clock cycle of a quantum computer. And you can see for 1,000 bit, that goes from being billions of years to like a month, right? And if I went a little bit faster, like a megahertz, which is quite reasonable for even current modern day computers, quantum computers, we're now down to like less than an hour, right? So this is the big power of quantum computer, that we are able to take a problem that scales exponentially for a classical algorithm, at least the best known classical algorithm, and we're able to make it almost basically manageable. Okay. And so that's where people got interested, excited, that we have the first type of algorithm that can actually demonstrably beat the best known classical algorithm. And that took off. The research has become, many algorithms have been found. There are questions of like, are they really going to give us enough of an advantage and so on? Those are obviously research questions, things that we have to figure out and solve. Okay. Okay, so I have assigned a reading for you all, which is, and don't think that you have to understand everything in these materials, these reading materials, but I wanted to get you started off in learning to read the literature. Okay, so this is a paper which talks about quantum computers and those physical realizations of quantum computers that we had a question about. So read through that. And again, as I said, read through it, figure out any sections that don't make sense to you, come back with questions. That's what this is about. And then the limits of quantum computers. So it's just as important because we are going to be scientific. We're going to be learning more than the average person. We want to know what the limits are, at least as we know at this point right now for quantum computers. We may find out that, later on that that's not true, but at least at this point, we should know where we think the limits of quantum computers are as well. Okay. So both of these are posted in the Canvas site, and I'll post a few homework questions on these articles. But really, it was just to help you to start reading and thinking about this and come back to me with questions the next time, and we'll talk some more about that. Okay. Do I have any time left? Oh, actually, I have a few minutes left. So I won't keep you much longer, but I just wanted to get started with a little bit of an introduction. So what is quantum, right? I mean, now we are going to get into actually what we're going to be doing. And before I get into even talking about, what is a quantum bit and how do we represent it mathematically, which I could do before I go into the mathematics of it, it helps to step back and think a little bit about where did quantum come from and what are some of the unique properties of quantum systems that enable a lot of the quantum computation and quantum information science that we're talking about. Okay. So the first thing we have to know about quantum is that it is the physics of usually small objects. Okay. Atoms, molecules, photons. Okay. Photons are particles of light. I'm sure most of you have heard of them. And the next question is, okay, so what is so different about physics at these length scales? One of the big differences that people had never expected or didn't understand before they understood quantum mechanics is that it suddenly turns out that energy and momentum comes in lumps, in like little packets, okay? And the size of these packets is governed by something called the Planck's constant, which is an important fundamental constant of nature. Okay. When you think about it, it seems kind of weird, right? I mean, when I'm walking on this floor, I'm just walking in a line, right? I'm walking in a continuous way. At every minute, every second, if I were to plot the position of, say, my feet or my body, my face, whatever, and I were to draw this on a graph, it would look like a continuous line, right? And the amount of energy that I have as I'm moving around, right? Well, if I start in potential energy, it's a constant because I'm on this gravitationally equipotential surface. But my kinetic energy is maybe fluctuating, but it's fluctuating continuously, right? So all of a sudden, as we reduce our length scale down to the size of atoms and electrons and photons, it turns out we can't do that anymore. The energy doesn't move in small continuous increments, okay? It comes in small lumps, okay? And the size of those lumps, as I explained, is governed by Planck's constant. And then, of course, this is the famous thing. We'll come back to this with some experiments and so on, is particles can act like waves. So, and I'll explain that in more detail, but basically this is the sum of this whole understanding that we have, that waves and particles, this description that we had for objects pre-quantum physics, they sort of start to blend together. So before quantum physics, there were particles, things like electrons, atoms, blocks of wood, beams, etc. those were like particles or planets. We could model them as particles given how big the space was. We could just think of them as like little particles in space. So, but waves were a very different thing. So that was, the waves of light and waves on the ocean, etc., sound waves. They behaved in a very different way than particles. They seem to be everywhere, right? You have a light wave. You can't really say the light wave is here or there. It seems to be everywhere, okay? So it turns out from quantum physics that when you get to the small enough length scale, particles act like waves and waves act like particles. Okay, this is just summarizing what I said a little while ago, that in classical physics, everything is made of particles or waves. I should have added that. But if I give you the initial positions and velocities of the particles, then I can predict all of their future positions. The universe is completely deterministic, okay? Except for chaos, but we won't worry about that for now. Yeah. And the failure of classical physics is pretty much, it was our understanding for 200 years, okay? Until about 1900. And then by 1930, we no longer believe that particles even have well-defined positions and velocities, okay? So a huge change in how we thought about the universe. And the conclusion of all this is that nature is fundamentally probabilistic. This is a big change. Einstein never agreed with this, okay? He never believed that this was true. But as far as we can tell, with all of our experiments, we have tested predictions of quantum physics to parts in trillion, okay? It's one of the most precisely tested theories of nature that we have. And we haven't found any deviations from it. So as far as we can tell, nature is indeed fundamentally probabilistic, okay? So we have to shift our way of thinking about the universe. So what happened? I'll leave that for the next class. So today we'll just conclude with that. Just to summarize, our second quantum revolution is underway. And it's an exciting time for quantum science and technology. I want you to take that away. Many architectures have been proposed, many qubits have been created for quantum computing, and we don't yet know which one is the winner. And that's still an area of active research. And the fundamental physics that underlies all of these advances is the physics of quantum objects. And we will do a brief exploration into quantum physics in the next lecture before we jump into quantum computing. Okay. All right. That's it for today. If you have any questions, let me know. Otherwise, I'll see you all on Friday.